Welcome back, everybody. So we are here in section 4.6. We're going to jump a little bit to the end of the chapter because it covers an additional approximation method called the trapezoidal rule. So let's just remember from 4.2, we had three different methods that we looked at. So left endpoints, right endpoints, and midpoints. So for left endpoints, let's suppose that we have a graph that is decreasing. So if we take that same graph across each one, we can subdivide our closed interval. So we'll start by just closing it off here. And we're going to try and measure the area under the curve. So maybe we have a couple of subintervals. So let's do 3. So if I do left endpoints, that means I would start on the left and mark those locations corresponding with the beginning of each subinterval. And then I would create a rectangle built from that left vertex. So if we did left endpoints, we would have an over approximation that would be 3 separate rectangular areas. If it were right endpoints, we would start on the right, and then our rectangles would be built from the right vertices there, and this would be an under approximation. So you can see from our notes before, we looked at increasing functions where we had a switching of the order. So whether the function is increasing or decreasing, as well as concave up or concave down, is going to affect our over or under approximation. So for midpoints are a little different. So for midpoints, we took the midpoint of each subinterval and constructed it from the height at that midpoint. And then we just calculated the area by doing the area of a rectangle, so length times width, where our widths were these fixed delta x lengths, and then the function value at that particular subinterval was our height. So we had all these f of x sub I delta x's. So what we're going to look at today is building our approximation with, instead of rectangles, trapezoids. So let's just recall that the area of a trapezoid is going to be represented by 1/2 base 1 plus base 2 times the height, or you can think of it kind of as the average of the two bases, so b1 plus b2 over 2 sometimes. So we're going to use this idea to construct our trapezoids. We're going to let h be our delta x, as you'll see in the picture when we write it out. And then these two base 1 and base 2 values are going to be 2 separate function values. So we're going to use the heights of the function actually as our base to build our right-angled trapezoids. So let's go ahead and go down and look at our first examples here. So I've already kind of pre-drawn the pictures a little bit. So we want to evaluate the integral from 0 to 4 of the square root of x dx using trapezoids with n equals 4. So we want to find the area under the curve approximated with trapezoids. So what I'm going to do for trapezoids is I'm going to mark every subinterval point here. So we'll just note delta x is going to be 4 minus 0 over 4, since n is equal to 4. So delta x is just 1 unit in length. So we go from 0 to 1 to 2 to 3 to 4. And then what I'm going to do is I'm going to connect those vertices with a line segment. And then after we do that, we can draw some verticals in. So we can see at each point there are going to be a trapezoid between any 2 subinterval locations. So there's 1, 2, 3, 4 trapezoids. You'll note for number 1, our base is 0, right? So it's 0 over here. So the trapezoid becomes just a triangle. So this can happen if your function is equal to 0. But everywhere else, we'll have our 2 bases, and then our height, of course, is delta x. So this would be base 1, base 2, and then our height is delta x. So let's go back. So now we're going to construct the area of each one. using that algebra that we can see here. So the area using trapezoids is going to be, again, using that area formula for trapezoids above, so 1/2 times h times the sum of the bases. So let's go ahead and do it kind of the long way, and then we'll see how we can kind of shorthand it. So we've got 1/2. So for our first subinterval, we'll have 0 plus, our function is the square root of x, so at 1 it's just going to be the square root of 1 times delta x, which is 1, plus 1/2, and then so that's going to be for this shape, and then our next one is going to be for this one, which is going to be 1 plus, so square root of 1 plus the square root of 2 times 1, plus 1/2 times the square root of 2 plus the square root of 3. So that's going to be for this subinterval. And then finally, plus 1/2, and then rad 3 plus rad 4, which again, we'll simplify in a moment, but we'll just emphasize that those are the function values. And that's going to be our last trapezoid there. Now, as we did with rectangles, we can really simplify it as the height times all of the sum of the heights. This one's going to be a little bit different in that it's going to be this 1/2 times delta x, right? So we don't just have base times height, we've got 1/2 and delta x. Oops, I forgot a delta x here. But we'll note for this particular example, our delta x is simply 1. So it's not really going to be a huge factor, but we'll just note it here. So we'll factor out 1/2 and 1 as our delta x value. And so what we're going to end up with then is the sum of all of those heights. And what you'll notice is that for every height in between that is not an endpoint, so is not our x0 or xn value, there's 2 of them, right? And so this is going to be really how we can generalize for these types of examples. This won't always be possible, but it is in this case. So this is really 1/2, and then 0 plus 2 times the square root of 1 is just 2. And then 2 rad 2 plus 2 rad 3 plus rad 4, which is 2. So now we can just fully simplify here. So we'll have 1/2. The 2 and the 2 I can combine, so I'll have 4 plus 2 rad 2 plus 2 rad 3. And then we can divide everything by 2. So we'll have 2 plus rad 2 plus rad 3, which we can leave exact or approximate with a calculator. So again, this is going to kind of repeat itself unless we can run into examples where we have uneven subintervals. So this first method that we do here, where we write each separate trapezoidal area, is just going to be required for certain examples. So just know that it only generalizes when delta x is a fixed value. All right, so let's look at the next example. So we've got the integral from 1 to 4 of x squared dx. So it's going to be the area bounded between 1 and 4. So we'll just close it off here. And again, we're going to do the same thing of marking each vertex. Oops, sorry. We've got 6 subintervals, okay? Which means we've got 7 dots here. And then again, we're going to do the same thing, connect those to build trapezoids. So we can see each one here. So we've got all of those areas accounted for. And then what I'm going to do here is, because we are using that fixed delta x, I'm going to just generalize our solution here. So the area of the trapezoid is going to be 1/2 times 1/2. So note this is a half, and then this is delta x, right? Which is equal to the height of each trapezoid. So each trapezoid's height, which is along the x-axis, is just 1/2 in length. And then that's going to be times each function value. So that's going to be f of 1 plus 2 f of 3 halves plus 2 f of 2 plus 2 f of 5 halves plus 2 f of 3 plus 2, let's actually see if we can do it all the way across here, plus 2 f of 7 halves plus f of 4. So what you'll notice here again is in the middle we have two function values for each separate trapezoid that's adjacent, but our endpoints only occur once because they're only going to occur in one trapezoid. And then now it just comes down to calculations. Our function is x squared, so we can work this out here as 1 plus 2 times 3 halves squared is going to be, let's see, 9 over 4 times 2, so that's going to be 9 over 2. And then 8 plus 5 halves squared is going to be 25 over 4 times 2 is 25 over 2, plus 9 times 2, which is 18, plus 7 halves is going to be 49 over 4 times 2, so 49 over 2, plus 4 squared, which is 16. Okay. And then we can kind of group these together. So I can group all the integer values together. So 1 and 8 makes 9, plus 18 is 27, plus 16 is going to be 43, it looks like. And then 9, 25, and 49, what is that going to give us? Well, it's going to give us 34 plus 49, which is 83 over 2. We'll divide that by 2, so that's going to be 41.5. And then we can divide that by 4, and so we're going to get 21.125, which is 21 1/8, I think. Which is the same as 169 over 4. So this would be an example where I would probably let you use a calculator, because the point is not necessarily that you can calculate these numbers quickly without the aid of a calculator. It's really writing out that trapezoidal rule. All right, so we've got that second example done. We'll move on to the third example here. So we want to evaluate from -4 to -1. So I wanted to give you an example where we're on the other side of the x-axis, which is, again, perfectly fine. Doesn't matter where we're located. You could reorient this as the integral from 1 to 4 because it is an even function, so you'd have symmetry there. So if you prefer from 1 to 4, that would be perfectly fine as well. In this trapezoidal case, though, we do have to be careful with if we're over or under approximating. So just be wary. If you don't have symmetry, you can't do that. So let's go ahead and mark off our vertices here. Just connecting. So we're going to have 4 trapezoids, it looks like. And this one, again, is also going to get messy, so you can definitely use a calculator for this one. So feel free to pause the video if you want to work this one out on your own. And so let's go ahead and get right into this one. So the area, trapezoidal approximation is going to be, let's see, so delta x is 3/4. So we're going to have 1/2 times 3/4 times, and then we're going to have all of those function values. So we're going to have f of -4 plus 2f of -13/4 plus 2f of -10/4 or -5 halves plus 2f of -7/4 plus f of -1 So it looks like we're going to get 3 over 8 times, and then our function is over x squared, 1 over x squared. So we'll get 1 over 16 plus, this is going to be 2 times 1 over 13 over 4 squared. So we're going to get 1632 over 169. And then we could use -5/2 here. So that's going to be 4 over 25 times 2, which is going to be 8 over 25, plus we'll have 16 over 49, so 32 over 49, and then 1 is just going to be 1. So if we put that into a calculator, definitely be careful with your parentheses here. So 1 over 16 plus 32 divided by 169 plus 8 divided by 25 plus 32 divided by 49 plus 1. And it looks like we get 0.83434133763. Just remember, you have to have at least 3 decimal places, so 0.834 would be perfectly fine as an answer, but you can also include more. All right, so these are kind of 3 standard examples that you'll see from the textbook as well. So for the generalization, let's just note that our general trapezoidal rule, if delta x is fixed, is going to be delta x divided by 2, so 1/2 times delta x. And then we'll have f of x0, where that's our a value, our left endpoint. And then we're going to have a series of f of x1s, x2s, x3s, all the way up to some second to last term, which we can call f of x to the sub n minus 1, plus, and then f of x sub n. So note where, oops, a is x naught and b is xn. So that's going to be kind of our generalization if delta x is a fixed value. So it's a really simple formula to follow, and as you use it more and more, it'll be simpler to use. But we'll look at examples, though, where delta x is not fixed, and then you have to go one by one and just compute each trapezoid separately. All right. So let's look at the next example. So this is going to be estimating velocity, estimating distance. So distance, again, is going to be the integral. So note distance is equal to the integral. In this case, we want the distance in the first 30 seconds. And so that's going to be the integral of the absolute value of the velocity, or the integral of speed. But no, we don't have to care really so much about the absolute value in this case, because our velocity is always positive. So we'll note here, v of t is positive everywhere. 0.3, so no absolute value needed. So we don't need any absolute values. But we can construct our trapezoids here. So we'll connect each one of our points here. I just estimated the points kind of from the graph there, from the table, sorry. So if you want to label the x and y axes, you can. So it's going to look something like this, but again, we've got even subintervals, right? So delta x is just 5, so it makes it much easier. So delta x is going to be 30 minus 0 over 6, which is 5, which is obvious from our table as well, but just to be safe. And so let's go ahead and calculate our area here. So area of the trapezoid is going to be 5/2. So again, 1/2 times delta x, and then we'll have f of 0. So we've got 25 plus 2 times 31, plus 2 times 35, plus 2 times 43, plus 2 times 47, plus 2 times 46, plus 41. Let's double check that. 2, 2, 2, 2, 2. There should be 5. Perfect. And then the numbers here are a little bit nicer, so they're pretty easy to put into our calculator. So we'll have 25 plus 62 plus 70 plus 86 plus 94 plus 92 plus 41. And that's going to be times 5 divided by 2. And so we should get 1175, and our units are feet per second, so this is going to be feet. So 1175 feet is the approximate distance traveled in the 30 seconds, given the information from our table. Okay, so we've got our last example, which is an actual AP question. There are some bits to it that we haven't quite covered yet, so in part C in particular, so I'll discuss that one, but no, we'll probably not have discussed that one in full detail by the time you see the video, so just keep that in mind. So we've got a pot of tea cooling, and the temperature of the tea is modeled by this differentiable function h, which we have a table of information here on. So we've got degrees Celsius for our table, and we know that it's between 0 and 10 minutes. So we want to figure out some information about this pot of tea as it cools. So if we look at part A is actually going to be a computation of the derivative, right? So it says use the data to approximate the rate at which the temperature is changing. So that's asking us to approximate the rate of change of the temperature, which is going to be h prime of t. So this is pretty easy to see from our table here. So h prime of t is approximately going to be, well, if we want to know at 3.5 minutes, we want to find the smallest interval that contains 3.5. And so clearly that's going to be between 2 and 5. So then h prime of t is going to be approximately h of 5 minus h of 2 all over 52 minus 60. So that is going to be our approximation. Clearly it's just going to be the slope between those 2 points. So we end up with, let's go back. Divided by 5 minus 2. I was putting the wrong values in there. So it's a 3-minute interval on the bottom. So our temperature change is going to be 52 minus 60. And then our time change is 5 minus 2. So it looks like we get negative 8 degrees Celsius over 3 minutes. So our approximation of the time of the temperature change is going to be that it's changing at approximately negative 8/3 degrees Celsius per minute. Now for B, this is where we're going to use the trapezoidal rule. And it asks us to explain the meaning of this integral, which we know that this is going to be the approximation of h of t. But what is this 1 over 10 business? So this 1 over 10 business is actually going to be something that we look at when we get to 4.4. So this is called the average value. And the average value in this case is the average value of h. So it's going to be the average value of h of t on that time interval 0 to 10. So this is going to tell us what the average temperature is on that time interval, right? And so we're going to take the approximation of the area underneath that height curve and divide it by time, so 10 minutes. So we'll get this degrees Celsius time measurement divided by time, which will give us degrees Celsius. So we want 4 subintervals as well. So let's go ahead. We can zoom out a little bit here just so we can still see the table. So for B, 1 over 10 integral of h of t dt from 0 to 10 is going to equal 1 over 10. So now we're going to use our trapezoidal rule, but note we have uneven subintervals, right? So we've got 0 to 2, 2 to 5, 9 to 10, etc. So we know that they're not even. So I would highly recommend in these examples where you're doing these uneven Riemann sums, draw a quick picture. You don't have to, but it can be very helpful just to see what your shape is going to look like. So we've got 66, 60, 52, 44, 43, something like this. We can construct our quick little trapezoids here. And that way you can just easily visualize each area. So this one we can't use the general rule for, because obviously we have uneven subintervals. So for our first trapezoid is going to be 2 by 66 plus 60. Oops. So again, we're still just adding those function values. So we'll have 1/2 times 2 times 60 plus 66. And then the next one is going to be 1/2 times 3. And then that's going to be 60 plus 52. And then we'll have 1/2 of 52 plus 44 times 4. So delta x is 4 here. So 52 plus 44. And then plus 1/2 times 1, since delta x is just 1, from 44 to 42. So 44 plus 42. And again, this would be a calculator example, so we can just add that up. Or actually, you could probably do this without a calculator if you wanted to. So let's go ahead and simplify a little bit here then, see if we can. So that's going to be 2. Okay. So we'll get 1/10, and then we'll have 126 plus, so 3/2, 60 plus 52 is 112. So 112 times 3 divided by 2 is 168. And then 2 times 96 is going to be 192. And then half of 44 plus 42 is going to be 43. So that's just the average. So that gives us our values. So let's go ahead and put those into our calculator here. Plus 168 plus 126 divided by 10. And so we get our approximation is 52.9 degrees Celsius, which given our table should make sense, right? 52 is right in the middle, and it looks like we're decreasing at kind of a steady rate. So it looks like those lower temperatures and higher temperatures are offsetting a little bit. So 52.9 degrees Celsius. And our answer here is going to be that the average temperature is 52.9 degrees Celsius from T equals 0 to T equals 10. And note for the AP, they want you to describe the exact description of the value. So in this case, average temperature of the pot of tea. Okay. And then finally, we have this C1, which is the integral from 0 to 10 of h prime of t dt. And so we're going to use the fundamental theorem of calculus to evaluate this. So this will make sense once we finish 4.4. But what the fundamental theorem says is that this integral can be evaluated by using the antiderivatives of h prime in this case. So this is going to be equal to h of 10 minus h of 0, which from our table is going to be 43 minus 66, which is equal to negative 23. Now h is degrees Celsius, so negative 23 degrees Celsius. So What this is telling us is that from the interval 0 minutes to 10 minutes, the change in the temperature in the pot of tea went down by 23 degrees Celsius. So the temperature in the pot decreased by 23 degrees Celsius from t equals 0 to t equals 10. Again, we want to be very specific about what we're describing. I did decrease. You could say the temperature in the pot changed by negative 23 degrees, but you have to indicate that it's going down with some sort of verbiage or adjectives. And then always, always, always put the time interval. So again, this is a direct AP FRQ question, so you can look through that and try that one again on your own if you want to. All right, so that concludes our trapezoidal rule. We're just going to do one big long video here. So if you do have questions, send me an email. Otherwise, come by and visit the office hours as well. And until I see you next time.